How can differences in a physical property be used to separate the components of a mixture? And how can the reactivity of those components affect their physical characteristics? I'm Amanda Swearingen, and these are a couple of the underlying questions we'll tackle during this lesson, specifically looking at solubility-based separations. Within the context of an experimental procedure using a separatory funnel, we'll explore how a single component of a mixture can be extracted. First, we'll focus on how a single physical property can dictate which one of two layers will dissolve a single component. Then, we'll see how a chemical property can be used to manipulate the physical properties of those components within the same procedure. This is a fairly long and complex question stem containing a lot of contextual supporting information, which is very similar to what you'll see on the MCAT. So take a minute or so to read the question and untangle the supporting information. The question stem starts off with an experimental problem. A student synthesized some aromatic compounds, but rather than producing pure products, the student has a mixture. Not only does the student have benzoic acid and 4-nitroaniline mixed together, but also contaminants, which are the leftover reactants. The experimental procedure we are concerned with is therefore how the student will go about fixing the problem of the mixture, resolving each of the individual components. And just like on the MCAT, whenever you have an experimental procedure, take it apart piece by piece. First, the student is going to dissolve the mixture in dichloromethane. Then, the student washes the solution, followed by a collection of the aqueous layer. Notice that the student performs this wash and collection step 3 times. First, with water, and then collecting layer A. Second, with sodium hydroxide and collecting layer B. And the third wash with hydrochloric acid, collecting layer C, which leaves one final layer at the end, layer D. Finally, the overall question focuses on which mixture component is located in which layer. But before we start the deduction process of which component is in which layer, let's first review how this separation procedure works. First, all separation processes exploit a physical property that is different enough between the components of the mixture. Extraction falls under the umbrella of separation processes, specifically isolating components from one another by transfer, where one component moves to a different phase than the other components. In this procedure, using a separatory funnel, you start with the sample, dissolved in one phase. Generally, this will be the organic layer since we are mostly concerned with organic molecules, but you should check what the sample is dissolved in to make sure. Then you add the opposite phase, which generally is going to be the aqueous layer. So how can you tell that the sample mixture in the student's experiment was in fact dissolved in the organic layer? First, recall that we were told in the question stem that the initial step of the extraction procedure was dissolving the mixture in dichloromethane, an organic solvent. But even if you weren't sure whether or not dichloromethane is in fact organic solvent, we also know that the mixture is mostly made up of benzene and aromatic derivations, which are organic compounds. If you're still not convinced, the next step, the first wash the student performs, is with water, which is most certainly an aqueous solution. Let's talk about those 3 washing steps. That involves mixing of our 2 layers and then allowing them to settle before collecting that aqueous layer. Importantly, the student performs this step 3 times for each of the 3 washes. While this may seem like a minute detail, in practice it's actually extremely important to perform a wash step several times. More washing then allows for greater interaction between the component and the aqueous phase, not only increasing the amount that can be extracted, but also increasing the purity of each component that we then collect. Now for the question of how this works. So, how can a separatory funnel be used to separate components of a mixture based on the differences in solubility? A single component can be extracted from the sample phase into the opposite phase based on comparative solubility. On one hand, the component has a greater affinity for the opposite phase compared to the original sample phase, where we have charged or polar solutes that are going to be pulled into the aqueous layer. On the other hand, the the other components remain uncharged and nonpolar, and so have a greater affinity for, and thus remain in the sample phase. This principle can be more easily remembered with the mnemonic like dissolves like. Now that we've reviewed how this procedure works, let's start deducing which component is extracted into each of the 4 layers the student collected. At the start, we have a mixture of 4 different components. Our 2 products, benzoic acid and 4-nitroaniline, and 2 contaminants, the unreacted starting materials, benzene and the electrophiles. Recall that the student dissolved the mixture in dichloromethane and then added the aqueous phase, water, and that was used to extract the first component of the mixture, which was then collected as layer A. Considering the makeup of our mixture, we can predict that the small electrophile contaminants will be removed from the sample organic phase during that first wash. So how do you know that the small electrophile contaminants will in fact be the first component extracted into the aqueous layer? By definition, electrophiles are at least partially positive, so they are charged, making them by far the most like water, as they are already aqueous. So the student was able to extract the small electrophile contaminants into layer A, since the other components in the mixture would not easily dissolve in water. But as sodium hydroxide is added to the mixture in the second wash step, the student is able to dramatically increase benzoic acid's ability to dissolve in the aqueous layer. Given the structure of benzoic acid from our question stem, when the student adds sodium hydroxide to the mixture, we can anticipate that these molecules will interact with each other in a very characteristic way. What will happen as a result of the interaction between benzoic acid and sodium hydroxide molecules? Initially, we know that benzoic acid was dissolved in the organic layer. Because the student adds a very strong base to the mixture, we can predict that it will interact with our acid by deprotonating it, leaving behind the benzoate conjugate base, which is negatively charged. Now that the molecules are charged, they have a greater affinity for the aqueous layer. So now we can see how we can also use chemical properties, such as characteristic reactivity, to manipulate the physical properties of molecules, using acid-base chemistry to deprotonate an acid, increasing its ability to dissolve in the aqueous layer, and thus, in this case, we were able to extract it into layer B. Let's take a look at another way we can use chemical properties to alter solubility. Looking at the structure of the other product in the mixture, 4-nitroaniline, we can see that unlike benzoic acid, the presence of sodium hydroxide would have no real effect on it, so it would remain in the organic layer. However, we can anticipate that it will be affected by the addition of hydrochloric acid, the final wash step. How does the addition of hydrochloric acid increase 4-nitroaniline's ability to dissolve in the aqueous layer and become less soluble in the organic layer? You might have anticipated that we are looking at the same acid-base reactivity, this time in the reverse. The addition of a strong acid will protonate 4-nitroaniline, leaving behind its positively charged conjugate acid, which as a charged molecule now has a greater solubility in the aqueous phase and a reduced affinity for the original organic phase. This allows the student to extract 4-nitroaniline into layer C, separating it from the last component, benzene, which is just going to be left behind in the final layer, layer D. In this lesson, you saw a lot more than just a separation procedure. You also saw how physical properties underlie the techniques used to resolve components of a mixture, as well as how we can further manipulate those physical properties using chemical properties to resolve those components, such as reactivity.